Hi everyone, this is Jake Fry again, and today I'm going to discuss limits. So, in describing motion, there are many cases when we are interested in the value that a vector approaches at the extremes. So for example, if we want to know the velocity of a ball that is slowing down as the time approaches infinity. And so we know eventually the ball will stop moving at this limit. It wouldn't unless it's accelerating, it wouldn't stop and then bounce back. We would know that it would slowly approach a limit of 0. So by finding first the functional form of the system to describe the motion, as in my previous video, we can then develop the mathematical formalism for what a limit is. So you might remember seeing things like this in your math courses, but just in case, in this mathematical form, we show the limit of the function f of x as x approaches the value a equals L, our limit. So in each of these cases, we have a function that looks very similar. It's this blue line. On the left is just the curved line as our function. In the middle, we have a hole where we've removed the point and placed it lower. And then on the right, we have a hole without a point itself. And so as x approaches the value of a, we're curious what happens to the limit. And in each of these cases, the function as you approach a from either the left or the right approaches the same value L. Okay. And so in the case where a different value is approached from the left or the right for a stepwise function, the format is a little bit different. So the x goes to a from the negative would be shown with the leftmost option. And then if you approach from the positive side, it'd have x going to positive a. And so then you can only actually write that the limit as x approaches a of f of x equals L without any pluses or minuses above the a, if and only if you approach the same value from the left and also from the right. And so I guess going back to this previous slide, we have each of these, when you approach a from both the left and the right, approaches the same value L. So in each of the three cases, we don't need the little positive sign above the a. Okay, and so now if we have multiple composite functions and we need to find the limit of the function itself, there are many laws of the limits. For example, the first one here, if you have two functions, f of x and g of x, that are added, then when you take the limit of the two functions, you end up with just the limit of f of x plus the limit of g of x. And similarly, which I guess it shouldn't really be a different law, if one of the functions is negative, then the limit of f of x minus the limit of g of x would be the answer. Cool. And so the next law would be if you multiply the function by some constant value c, then your limit is just c times the limit of the function itself. Cool. And then next, if you have two functions that are multiplied together, then the limit of that composite would be the limit of f of x multiplied by the limit of g of x. And then lastly, if you have two functions that are divided by one another, then the limit of that division is just the limit of f of x over the limit of g of x, so long as the limit of g of x does not equal 0. All right, so now a few more rules. So the limit of a function that's raised to a power n would be the same thing as the limit of f of x raised to the power n. And so you can see this one by, I guess it would be rule number 4. If you keep repeating copies of f of x, then each of those limits would be multiplied by each other, in this case n times. And then I guess the next one, the limit of a constant is just the constant itself. The limit of the variable x as x approaches a number a is just a. And then the limit of x raised to the power n is just a raised to the power n, where n is a positive integer. All right. Now the next one, the limit of the square root of n of, the limit of x to the square root of n equals the square root of n of a. And that's if n is even. We assume that a is greater than 0, because otherwise we would have an imaginary number. And then the limit of the nth root of f of x is the same thing as the nth root of the limit of f of x. Again, we assume that what's under that nth root, if n is even, must be positive. Okay, so for some of these rules, we saw a important property to find the limit of a function. So if a function f is a polynomial or a rational function, and the value a is within the domain of f, then you can just directly substitute x for a to get what the limit is. Okay, and so a few more theorems. So if f of x equals g of x when x does not equal a, then the limit of x, as x approaches a of f of x equals the limit of x approaching a of g of x, provided that the limits exist for those functions. Okay, so next theorem would be that the limit as x approaches a of f of x equals L if and only if you approach that limit from the left and the right. And so we saw this one before in our first example. All right, and then the next theorem is that if f of x is less than or equal to g of x when x is near a, except possibly at a itself, and the limits of both f and g exist as x approaches a, then the limit of f of x is always less than or equal to the limit of g of x as you approach a. And so that theorem allows us to define a new one, which is quite useful in finding theorems of difficult functions. Finding limits of difficult functions, and it's called the squeeze function. So we extend it with one more interaction, in this case h of x, and so we find that the limit of f of x would always be less than the limit of h of x, and g of x would always be greater than f of x. The limit of g of x would always be greater than the limit of f of x as well. And so you would squeeze the limit into an unknown, from an unknown region for what g of x could be into a region where it must be. So because if you have the case where f of x's limit equals h of x's limit, then g of x's limit will be squeezed down to have the same value. And so that's known as the squeeze theorem. So yeah, so with all of these theorems and also laws regarding limits, we can now, for pretty much whatever type of physical function that you have, try to figure out what the limit is. Typically at long time is what we in physics care most about. But with the formalism of limits, we can motivate in our next lecture an incredibly important tool for physics itself, which is calculus. All right, thanks.